Welcome to API Delevan's Continuing Education Series. The program you have selected is an Introduction to Passive Magnetic Products. In the next half hour, you'll learn the essential terminology used in the design and selection of inductors, chokes, transformers, and related products, plus the basics of operation, performance characteristics, and product applications. Let's begin with some of the terms frequently encountered in passive magnetics. Inductance, quality factor or Q factor, test frequency, direct current or DC resistance, self-resonant frequency or SRF, current rating, and incremental current. Inductance, or symbol L, is the opposition to change in alternating current flow in a coil of wire. Anytime current passes through a coil of wire, the result is a magnetic field. The magnetic field stores energy much like a capacitor, but an inductor, by comparison, stores energy within its magnetic field for use later in a circuit. This ability of a coil of wire or a winding of wire to store energy is called inductance. A coil is not necessarily round. It can be square, or elliptical, or spiral. The basic unit of measure of inductance is a henry. Most frequently, products are measured in millihenries, or 1/1000th of a henry, microhenries, or 1/100000th of a henry, and nanohenries, or a billionth of a henry. Energy in a magnetic field is calculated by a simple formula: Li squared over 2. L is the inductance, and I is the current divided by 2. The result of this equation is measured in joules. Measurements for modern inductor designs are frequently expressed in millijoules and microjoules. Here's a graphic representation of current in a coil. The green symbol is a sine wave depicting an AC current flowing through an inductor. The dotted lines represent lines of flux or the magnetic field of the inductor. Each one of these lines of flux passes through the center of the inductor core, regardless of the core material and regardless of inductance. Lines of flux can be beneficial in an application such as a sensor intended to detect mechanical motion in a device. But in most inductor applications, lines of flux are detrimental because flux creates electromagnetic interference, or EMI, with other components on the circuit board located in close proximity to the inductor. API Delevan offers shielded products designed to contain lines of flux. API Delevan offers a full range of tolerances for its inductor product line. An inductor's tolerance is the amount of variance allowed from a particular inductance value. The inductance values offered by API Delevan as standard products are shown as the nominal inductance with the percentage of variance from the nominals permitted by API Delevan. Typically, a K or a plus-minus 10% would indicate a general tolerance often found in RF products. An M tolerance or an L tolerance at 20% or 15% is popular in power products. Applications requiring extremely tight tolerance, such as crystal oscillators and phase lock loops, demand 1 and 2% tolerances, indicated by F and G. Perhaps the least understood of all the terms in the industry is Q. The symbol for quality factor, Q, is a measure of relative losses of an inductor at a given frequency. Q is specified as a minimum, not as a plus or minus, and not as a maximum. Here are the most frequently used formulas for calculating Q. The most frequently used formula is Q equals X sub L over R sub AC, or the inductive reactance divided by the AC resistance equals Q. Q meters such as HP 4342A or 260A measure Q by direct reading. Meters including the HP 4191 and HP 4291, 4285, and 4275 read Q as a comparative measurement. The purest and most accurate way to measure Q is with a direct reading Q meter and not on an LCR meter or on a comparative type of bridge. Test frequency is an arbitrary frequency originally determined by the DoD. The military required that certain ranges of inductance values be tested at given frequencies and are within the blue line frequencies range of the Hewlett-Packard Q meters. Most test frequencies are multiples of 2.5, such as 0.25, 2.5, 25, and also 7.9, such as 0.79, 7.9, and 79. Test frequencies on a comparator are generally round numbers like 1, 10, or 100 in kilohertz or megahertz. Test frequencies should not be confused with the frequencies encountered when an inductor is used in a real-world application. Because test frequency is an arbitrary number, it is only useful for manufacturers and their customers when evaluating inductors. Again, test frequency is normally specified in gigahertz, megahertz, or kilohertz. Remember, gigahertz is a billion, megahertz is a million, and kilo is 1,000. Direct current resistance, or DCR, is the opposition to the flow of direct current in a magnet wire that changes electrical energy or current into heat energy stated in watts. DCR is measured in ohms and determines the amount of power dissipation an inductor can withstand. In other words, the amount of watts that an inductor can dissipate is based upon the amount of current going through it and the amount of heat energy that the opposition to the current flow creates. DCR is specified in ohms, milliohms, or kiloohms as a maximum. DC resistance is normally rated at 25 degrees C or 77 degrees F. Because magnet wires are copper, their resistance goes up as the copper heats up. A baseline is established at 25 degrees C. In custom engineered products, 20 degrees C is often used. In those cases, designers convert based on the coefficient of copper to what the reading should be at 25 degrees C. DC resistance is critical for determining power dissipation expressed as the current squared times the DCR at 25 degrees C. Again, the baseline 25 degrees C is important because power dissipation changes proportionally as temperature changes. Power dissipation is measured in watts, current in amps, and DCR in ohms. The self-resonant frequency, or SRF, is the point where an inductor will act as a pure resistor, with no inductance and no capacitance. In actual inductor applications, the SRF is a much more important value than the test frequency, because the test frequency is only a guideline for assessing the suitability of one inductor over another. The self-resonant frequency is the limit above which an inductor is not normally applied. Below the SRF at a given frequency, an inductor will perform properly, but above the SRF, an inductor behaves like a capacitor. The SRF is normally specified in megahertz, gigahertz, or kilohertz as a minimum. The SRF is easily calculated. SRF is equal to 1 divided by 2 pi times the square root of L divided by C, L being the inductance, C being the capacitance. SRF specifications are vital to determining how well an inductor will work in a given circuit. Frequencies near the SRF point are not normally usable because the inductance value is unstable. Here are performance test curves showing 5 different inductors. The inductance values can be seen at the top, 2.7 to 8.2 microhenries. Remember, the higher the inductance, the lower the self-resonant frequency. Note that at higher frequency, performance is more nonlinear. The test frequency shown here is down in the flat area where the line is drawn at 7.9 MHz. So the test frequency is found in the linear or flat position of the curve, and not in the severe slope of the curve. Optimum inductor performance is achieved in the linear portion of the curve. The curves show inductance increasing dramatically and then falling to zero. Finally, inductance goes down dramatically at the SRF point. The application frequency of an inductor should be no greater than 1/2 of the self-resonant frequency. So, if the SRF is 40 MHz, the inductor should not be used much over 20 MHz. Once above 1/2 the SRF in a circuit, a great variance in inductance is experienced, creating undesirable operating characteristics. Current rating is the value of DC that will cause no greater than the specified temperature rise, indicated by the symbol delta T. Current rating is represented by the symbol large I, or large I small dc. Most inductors are rated in DC compared to AC or RMS current. As we have seen previously, when a DC current passes through a piece of wire, the wire gets hot. The greater the current, the hotter the wire becomes. If the wire overheats, it burns up and, more likely than not, burns a hole in the circuit board. So current rating can also be thought of as the maximum amount of direct current that can safely pass through an inductor. The temperature rise, or delta T, sometimes called T small r, is absolutely critical. It's a design criterion unaffected by manufacturing processes, quality, or materials. IDC is not the saturation or incremental current rating. These terms are often confused because not all manufacturers use the same terms of reference for current ratings. Incremental current is expressed as small d, capital I, and is the same as saturation current. Incremental current is the change of inductance due to the amount of current passing through the inductor that will cause a decrease in inductance, typically in the range of 5 or 10%, compared to its zero current or zero DC inductance value. Current is specified in amps or milliamps, but rarely in microamps. When DC is run through a typical 10 microhenry coil as an example, a performance curve would look much like a person's leg when seated, flat to a certain point, reaching a knee, and finally bending down sharply, nearly at a right angle. It's very important to know where this knee is when evaluating inductor performance. The knee is the amount of current that can be applied while continuing to maintain the stated inductance value of the inductor. In other words, the limit of current at which saturation will not occur, resulting in loss of inductance. Some manufacturers will use 5% consistently. Others use 10%. API Delevan uses both, depending on the type of product and the application. Returning to this earlier illustration, remember that each one of these lines of flux will pass through the center of the inductor core. Depending on the core material and the amount of current, a point is reached where no current lines of flux can pass through the center of the core, regardless of the amount of current increase. That is the point of saturation. As the current increases, the inductance will decrease.